Chapter 4 gives us our first real application of thermodynamics to the subject that really brought it up, that helped develop science, which is engines. And there's a lot of experimentation going on with how engines work, which led to a lot of the development of the topics that we've already discussed. This is going back in the 17 and 1800s. So, what is a heat engine? How do we distinguish it from any other kind of engine? Well, if we're thinking in terms of a modern gasoline engine, that's an internal combustion engine, then it's, think of how to say this. A heat engine is a kind of engine in which it runs by drawing in heat from what we call a hot reservoir and converting that to useful work and then dumping waste heat into a cold reservoir. Now the hot reservoir and cold reservoir, in principle, could be anything. They need to be, when we say a reservoir, we mean a substance that is massive enough that it is able to give off or take in a little bit of heat to the engine without changing its own temperature. So the air, surrounding air, is generally a cold reservoir for engines. So you've got radiators that dump their waste heat into the atmosphere. Hot reservoirs could be, in the case of a gasoline engine, it could be the burning gases themselves. Well, that sort of obscures the somewhat cleaner design, simpler design that we've got in this chapter. Or it could be in a steam engine, it could be the fire in the firebox, and that transfers heat into the water in the steam engine's boiler, or whatever. Nuclear reactor, which is another kind of steam engine, has the radioactive material be the high temperature reservoir. So as long as you've got a substance that is it's at some temperature and it is massive enough that small amounts of heat can be taken from or given to your engine without the reservoir changing temperature, that's what we mean by a reservoir. Okay, so let me draw a diagram here of the basic schematic of a heat engine. So you've got some reservoir, some mass of material, water, air, the hot gases themselves, at a high temperature, T sub H. This is our hot reservoir. Okay. And we've got a cold reservoir. I'll draw it down here. Colder temperature, T sub C. Now, the normal way, natural way that heat would flow would be from hot reservoir to the cold reservoir, just by the normal workings of nature. Like that. That would be the heat flow. Fine. You take a cube of ice, you set it on a room temperature table in the kitchen. Heat will flow from the hopefully warmer kitchen into the cube of ice, which will melt it. Now, of course, the cube of ice is it's going to raise its temperature there, but heat flows from hot to cold. Okay, so what can we do? It turns out we can actually produce useful work by interrupting that heat flow and extracting some of the energy that would flow in the form of heat there and turning it into work. Remember, energy can't be created or destroyed, but it can change form. So we interrupt this and turn it from that energy from flow of heat into work. Find my eraser. Okay, so There, that's how we're going to do it. Well, not that I'm describing the details here. Let's take the amount of heat that flows out of the hot reservoir and call that Q sub H. What we'll call waste heat that's dumped into the cold reservoir will be Q sub C. Let's see if that's actually visible there. Yeah, I believe so. Okay, and then the useful work that's spun off of this will be W. Okay, and this device in the middle is our heat engine. Okay. Now, you've got to be careful in the terminology, because when we have been looking at the system in the previous chapters, and we've looked at, say, the work done on the system. Remember the first law of thermodynamics, du equals Q plus W. Change in the system's energy, U, is equal to the heat flow into the system, that's the positive sense, plus W, the work done on the system. Also, that's the positive sense. So if energy is added to the system through the flow of heat, then Q is positive. If work is done, if energy is added to the system through a compression, then W is positive. But in this case, in an engine, what we care about is not what's done to the system, the gases inside the engine. What we care about is what that system does for us. What does it do to the surrounding world, the surrounding universe, the outside world? So, W here is going to be the work the system does on its environment. We're actually going to switch the signs. QH and QC, you see, is actually so much more convenient to analyze this, where we simply treat QH, QC, and W all as positive quantities. Then if we had to worry about the signs on them, which is going in, which is going out. So for this chapter, QH, QC, and W will always be positive. And furthermore, an engine goes through cycles. If we say we take a canister, why does it go through a cycle? Well, it wouldn't be useful otherwise. If we took a cylinder with a gas in it and a piston that can slide up and down, we take that cylinder and we have it very compressed, or the piston is very low down here. We put a rock on it. Say we want to lift rocks with this cylinder. Okay, so we could put the cylinder over a fire. It would, heat would flow into the cylinder, into the gas. The gas would expand, and it would push that rock up. It would do useful work for us, and we could lift that rock up and put it up on an ice shelf or whatever. But if we want to keep going, if it's not just a one-time deal, we've got to get back to that initial state for the next rock. It's got to go through. So an engine has to return to the state it began in. So it has to go through a cycle. In fact, if you graph out its pressure and its volume, a PV diagram, the path that the gas will make around that PV diagram will form a closed loop. It has to come back to where it started. Otherwise, it's of no use to us, or very little use. So, to be more specific then, W represents the work done by the system, by the engine, on the outside world per cycle. The work per cycle. And QH and QC are the heat taken in and the heat dumped back out per cycle. So, all are positive. I think I better move the camera over slightly. Of course, this is when the battery fails. all three of these are positive, and they are per cycle, energy per cycle. So how many joules are taken into the system, to the engine per cycle, how much work in joules is done by the system per cycle, and how much waste heat is done in joules per cycle. Okay, let's see here. So this is notation for this chapter. Now, it's going to be useful for us to define the efficiency of the engine. How good is it at turning this difference in temperature into useful work? So, in principle, what do we mean by efficiency? Well, we use a lowercase e for efficiency. Some books will use lowercase epsilon. And efficiency is going to be defined as the benefit we get from this engine divided by the cost of what it takes to run it. Now, it may not be in dollars, but in terms of energy. So, benefit over cost. Okay. Now, the benefit, the whole reason for having a heat engine, is the work per cycle we get out of it. Okay? So it's the work out divided by, well, what does it cost to run the thing? We've got to suck in some heat. How much heat has to be drawn into the system per cycle? That's the cost. Okay. Well, that is our most basic way of expressing the efficiency, but it may not be the way that we need in some situation. Perhaps we want to express it in terms of the difference in the heat drawn in versus the heat that's dumped out. The QC is sometimes called the waste heat, for example. So let's see if we can re-express this in terms of just the heat flow. Now, turn this around a little bit more. Okay, first law of thermodynamics says that du equals Q plus W. Now, we've got to be careful about the sign convention. So let's put this in terms of the change in the system's internal energy per cycle. This may not show up well. This is du per cycle. Change in energy per cycle equals, now, the total heat flow, net flow into the system is how much flows in versus how much flows out. Minus how much flows out. That gives us the net increase in the system's energy on account of heat flow. So that'll be QH minus QC. I need one more click to the right. And because work per cycle has a sign that's positive for the energy flowing out of the system there. Okay, so I've translated this now into our engine design conventions. Okay. Now, I said the heat engine, to be useful, must return to its starting state after each cycle. So, what is the change in the system's internal energy after one complete cycle? Nope.
After one cycle?
What's the change in its energy from the beginning to the end?
Zero.
Zero, exactly. And by the way, remember that U is proportional to T. Energy is proportional to temperature. So, from the equal partition theory. So, we know that it's got to return to its starting temperature as well. Okay, so 0 equals QH minus QC minus W. We arrange and solve for QH, the heat that flows into the system, and that gets us QC plus W. Now that's actually a nice little result right there. The heat that flows in is equal to the heat that flows out plus the work done. That's just conservation of energy. We had to say that it returns to its starting point there, and then we get the fact that the total coming in equals the amount going out by both of these channels here. Waste heat and through work. Okay, good. Also means we can solve W, the work done out, in terms of the difference of the heat flow. Nice. By the way, I really ought to box that in there. That's a useful relationship to keep in mind. Okay, so the work done equals QH minus QC. Let's put that into our efficiency equation. Efficiency equals QH minus QC over QH, divide through. One minus QC over QH. So what does that tell us about the possible range of efficiencies, given that we've got the conservation of energy? Well, the minimum efficiency would be if there was no work done, then the waste heat QC would be equal to the heat that was intake, the intake heat QH. If all of the heat flows straight through the system without doing any useful work at all, then QC equals QH, and you've got 1 minus 1, which is 0. So the minimum value of the efficiency is 0. What's the maximum value of efficiency? Well, imagine that in principle you could take, say in principle, turns out it's not true even in principle, but what if you could take all of the energy that flowed into it in the form of heat, turn every last bit of that into useful work, W, and have no waste heat whatsoever? In which case QC would be 0, and you'd have 1 minus 0 equals 1. Turns out that's impossible, so I'm putting it's less than 1. It's not less than or equal to. We can get, through very good engineering and certain temperature differences and so on, we can get close to 1, maybe, but we can't get all the way up to it. So, the efficiency would be equal to 1 if we could get rid of all the waste heat. But can we get rid of all the waste heat? So, let's see our next little bit here. Slowly and painfully zooming in there. Okay. All right, so let's see what we can, what further constraints we can put on the efficiency by looking at the second law of thermodynamics. Among other things, the second law of thermodynamics says that the change in the total entropy, when you consider the engine and its surrounding environment, must be greater than or equal to 0. That is, the total entropy of the universe over any process must at least stay the same or increase, which is actually much more likely. That is, the total entropy of the universe can never go down. Okay. Well, the universe consists of the engine and everything else. Seems a little bit self-centered way of looking at things, but it's true. The entire universe consists of what I'm holding in my hands and everything else in the universe. Okay. Well, everything else is just the environment surrounding the engine, even at far distances. Okay. So the total entropy can never decrease, which means delta S is greater than or equal to 0. Okay. Now, since the engine's state at the end of its cycle is equal to the state at the beginning of the cycle, because it goes through an actual cycle, then the entropy that is expelled from the engine, okay, it takes in entropy, and when it takes in heat, entropy flows in with the heat. It expels waste heat, so there's entropy that flows out. With the heat there. Now, since the entropy that is expelled from the engine can't be any less than the entropy that went into the engine. Otherwise, we would have gotten rid of some entropy of the whole universe. Then, therefore, the entropy expelled from the engine must be at least as much as the entropy that the engine absorbed. Okay, how can we put that in terms of the heat flow? Recall equation 3.48. .48 says, for a quasi-static transformation, Q equals TdS. And I'm not going to write for quasi-static, I'm just going to say it here. Therefore, delta S is Q over T. Very useful to keep in mind. We're going to be using this quite a lot here, because all of our practical engines are going to have quasi-static transformations. Okay, so let's put that in here. That means, let's see here, the change in entropy, at the cold reservoir, that's for cold, is greater than or equal to, well, let's see, I should say the change in entropy through the process that expels entropy, that's at the dumps waste heat in the cold reservoir, is greater than or equal to the change in entropy for the process where the engine absorbs heat from the hot reservoir. Now let's apply delta S is Q over T. That means the heat dumped in the cold reservoir, the waste heat, over the waste heat's temperature, the temperature of the cold reservoir, I mean, is greater than or equal to the heat that flows into the hot reservoir divided by the hot reservoir's temperature. So you just apply that right there. Okay. Now, if I rearrange, let's say I get all the Q's on one side and all the T's on the other. So what's the ratio of the heat flow compared to the ratio of the temperatures? All right, so I cross-multiply, and I get, let's see here. I'm going to run out of room at the bottom. I'm going to move it a little bit to the left. There we go, that's better. waste heat divided by the input heat is greater than or equal to the ratio of the cold reservoir temperature to the hot reservoir temperature. Okay? Just from that right there. Now, what does that mean for our efficiency? Our efficiency was 1 minus QC over QH. So, if we put this in terms of TC over TH, we know that if efficiency is equal to 1 minus this here, then efficiency must be less than or equal to, so let's see, this is, therefore, efficiency must be less than or equal to 1 minus TC over TH. This gives us a hard and fast upper limit to the efficiency of a heat engine operating between these two temperatures. And the really convenient thing is that you generally will know what those two temperatures are. Okay. Now, if we could get our cold reservoir's temperature down to absolute zero, then the efficiency would be 1 minus, or the upper limit to the efficiency would be 1 minus 0 over TH, which is 1. In principle, then, we would be able to get up to an efficiency of 100%. But the second law also says that we cannot get down all the way to absolute zero. We've always got to be at least infinitesimally above that limit. Okay, so since our lowest temperature must always be greater than absolute zero, we will never get to an efficiency of 100%. So that constraint will get rid of that equal sign, and we know the efficiency is always less than this here. Okay. Well, the efficiency is always less than 1. I mean. So, an example, putting in actual numbers. I carve a little space off here. What do we actually have then for real-world cold and hot temperatures? In practice, your cold reservoir's temperature is determined by your surrounding environment. If you're running a heat engine, well, in the room here, the lowest temperature you can practically get is going to be the room temperature. So TC is usually going to be on the order of 300 degrees Kelvin. Now, if you're running it in the Arctic, terrific. You can actually increase the efficiency because you can expel that waste heat at a colder temperature. The outside is much colder. Engines run better when they've got that much colder temperature to expel the waste heat. Okay, so TC is determined by your environment. TH, on the other hand, is determined by the whatever it is you're using to generate heat, and that is partly a matter of what fuel you burn, or whatever other source of intake heat you've got. It's also determined in part by metallurgy. Your engines are generally going to be made out of metal. Well, you can't have a high temperature that is so high that your engine melts or deforms or whatnot. So, upper limit on TH then is determined by metallurgy and by your fuel source. Okay, so as an example, let's say you've got a heat engine that's running from a cold temperature of 300 degrees Kelvin, room temperature, reasonable enough, a high temperature reservoir of 500 degrees Kelvin, which is not really all that terribly hot. This is, to tell you the truth, I'm not entirely sure what a car's high temperature is going to be. But this is well within reason here. So what's your efficiency going to be in this case? 1 minus TC over TH, and your efficiency must be less than or equal to that. 1 minus 3/5, of course the units cancel out, and you get your efficiency must be less than or equal to 0.40, meaning 40%. Well, that tells you how high you could get it. Doesn't mean you actually will achieve that kind of efficiency. In fact, in practice, it's easy to get less efficient than this. If you have an engine which has it's not well lubricated, it's got friction, you're generating extra entropy by converting some of your kinetic energy and the motion of the engine parts into heat. You generate more entropy that way, and you lower your efficiency. So having a poorly machined or poorly lubricated engine will lead to a lower efficiency. For that matter, your choice of design could lead to a lower efficiency as well. And in fact, let's see how you could get your maximum efficiency out of an engine. How can you design an engine that will get you the maximum possible efficiency? Okay. The Carnot cycle is a cycle for how an engine can work that, in theory, can achieve the maximum efficiency. Achieving it in practice is another matter because you've always got lubrication issues, things like that. Friction, there's always going to be some friction and so on. But in theory, the Carnot cycle would allow you to get your maximum efficiency. It was named for the French physicist Sadi Carnot, which is why we don't pronounce the T. Okay. The problem we're trying to solve is how to get the maximum efficiency for a heat engine given a certain Tc and Th, the two operating temperatures. First, recall our equation for the efficiency. Given the second law of thermodynamics constraints on the entropy there. So we know this now, we just derived it. And we're also given for this problem the fact that delta SC, the change in the entropy when you're dumping the waste heat, must be greater than or equal to delta SH, the change in the entropy when you're taking in the intake heat. So you are never going to lower the entropy of the universe in the process. So at best, you might keep the entropy the same, and in practice, you're really going to be increasing it. That's what that means. Okay, because for a quasi-static process, Q equals TdS, then delta S is Q over T. So QC over TC is greater than or equal to QH over TH. Okay. Now, tell me the truth, because there are several steps to this, 4 steps to it, let me start back over on the other chalkboard so I can get all of this in, if not one frame, then close to it. What would really be nice would be to have this camera programmed with some settings where I could just tell it start back on this this chalkboard, and it would zoom back in at the proper zoom in the right positions. first, let me draw out, remind you what the PV diagram looks like. Let's see here. Okay, pressure versus volume. And remember that when we integrate changes of pressure over volume, we get the work done. So that's another value of the PV diagram for an engine. Okay. Let's see. For constant temperature, changes at constant temperature, we can plot what I call the isotherms. All the places on this diagram that are at the same temperature. So let's draw in where the low temperature reservoir's temperature is. This is a hyperbola. TC. And let's plot all the points that are at the high temperature reservoir's temperature, TH. This is a somewhat flatter hyperbola. Okay, roughly at least like that. Okay. Now, step one. We're going to absorb some heat from the high temperature reservoir. Absorb QH from reservoir at TH. Temperature high. Now, we want to avoid making any new entropy. This is how the book phrases this. There's going to be entropy created in practice as there's a transformation from, let's see here, as we absorb heat. Remember that, I'm going to think how to word this right here. We don't want to make any additional entropy in the transformation as it goes from the hot reservoir into the engine. So if we had, remember that with change in entropy being Q over T, if we were to take our hot reservoir temperature, high temperature here, that same amount of heat, when it goes from a very high temperature into a system at lower temperature, heat flows from hot to cold, the entropy that it brings in would be greater than what it took out of the high temperature reservoir, because the temperature of that system would be lower. Same flow of heat, Q in the numerator, but a smaller temperature, T, in the denominator, inside the system. So delta S becomes greater as it flows into the system. We don't want that. We want to get by with the minimum amount of entropy created as possible. So how can we avoid making any new entropy? We make sure that the temperature of the gas in the system is at the same temperature as the high temperature reservoir. Okay, so delta S sub gas, this is the gas in our system, is equal to the heat that flows into the system. Now, we've got a gas inside the engine. It's called our working fluid. In practice, it's actually a gas. But we call it a working fluid. The change in the gas's entropy, this is all contained within the system, is equal to however much heat you absorb divided by your gas's temperature. Okay. The amount of entropy lost by the hot reservoir, RES, I'll abbreviate for reservoir, is, now it's losing heat. So, negative QH, because that's the heat that flows out, divided by the temperature of the hot reservoir. Oh, that's TH. So we want, at best, we want however much entropy the reservoir loses is the exact amount that the system, our engine, gains. We want to set those two equal to each other. I've got a negative sign there because the reservoir loses what the engine gains, the gas gains. In order to do that, QH is the same on both sides. It means that the temperatures have to be the same. Okay. So we need our engine's gas to be up to the temperature of the high temperature reservoir. How are we going to get any heat to flow into the system if the gas is the same temperature as the reservoir? It's not actually going to work, is it? Heat only flows from hot to cold, naturally. In practice, then, we really are going to have the gas's temperature be infinitesimally lower, just a little tiny bit cooler than that of the high temperature reservoir, so that it actually will absorb some heat. Otherwise, it just won't. Okay. So, what happens then? So we've got heat flows into the system then. Now, as the gas in the engine absorbs that heat, well, if we're not doing it, everything else we're held constant. We're not doing any work on the system, whatever else. As you absorb energy through the flow of heat, the temperature would go up. And we can't really have that because then it won't absorb any heat. Okay, because we're right at that limit there. So, in order to hold the temperature constant, while we let that heat flow in, what are we going to have to do? Well, not cool it. We want it to hold constant, but something that would, under other circumstances, have cooled it, we let it expand. Now, if we let it expand at a constant temperature, so it's absorbing heat, which wants to make it expand, you know, normal things, keeping that temperature constant, that's an isothermal expansion. So, step one is an isothermal expansion. EXP for expansion. At the high temperature, TH. Okay. That's step one. Now, okay. And you can show from the first law that if you're holding the temperature fixed, you're holding the internal energy fixed, and if the temperature is fixed, then du is 0. And from the first law, that's equal to QH plus the work done in step 1. Noting the sign I've got here. Let's see here. And so you would get the heat flow in is going to be equal to negative W1, negative of the work done in step 1, which is going to be positive pressure along this step 1, dV, and it's a change in volume. Okay, so you have a function of how the pressure changes, that's that hyperbola there, integrated over this change in volume, which means that the change in volume in step 1 must be positive. You've got an expansion. This is just the mathematical proof of what I had already said. Okay, and there we go. Step 2. we've got to get the temperature of the gas down to the cold temperature reservoir's temperature, down to that cold temperature Tc. Now, we need to do this without changing the entropy. We don't want to increase the entropy in the process. So, we've got to get from here down to here in order to avoid making new entropy, which is always foremost in our mind. Okay? We don't want any heat to flow in or out of the system, because that would mean a change in entropy. Because, let's see. For a quasi-static process, which all of these will be, delta S is Q over T, all right? So if we don't want the entropy to change, we've done everything we can to avoid that here, then we've got to make Q equal to 0 in step 2. We've got to decrease the temperature while not allowing any flow of heat to avoid any change in entropy. What does it mean if Q is 0? That's called an adiabatic process. Okay? Now, in order to get down to this temperature here, we're going to have an adiabatic expansion. Because, now why expansion and not a compression? Because an adiabatic curve on the PV diagram curves down and to the right. So to make an adiabatic decrease in temperature has to be an expansion. There's our adiabatic expansion. It's a steeper curve than an isothermal process is. And it goes from a high to a low temperature when you're expanding. Great. That's our cycle. In step 3, we need to get rid of the waste heat at the cold temperature. Okay, how do we dump the waste heat while not creating any new entropy? Just as before, I note that delta S is Q over T if it's quasi-static, which this is. So the change in the gas's entropy is going to be, keeping a track of the sign, if we're dumping energy, we're losing energy, and QH and QC are always positive, we're going to have a negative QC over T sub gas. So that's how much the gas's entropy will change when we dump this much waste heat at whatever temperature the gas is in. Now the reservoir will gain an amount of entropy, QC over TC. That's a positive number. It's gaining it because it's gaining the heat. Okay, so in order to avoid making any new entropy in the universe, we set these. The change in the gas's entropy is equal to negative of the change in the reservoir's entropy. Whatever one gains, the other loses. Whatever one loses, the other gains. Okay? Therefore, since QC is equal to QC there, we have, this means we must expel the waste heat QC at a temperature Tc in order to avoid making any new entropy in the universe. However, if these two were at exactly the same temperature, there would be no heat flow between them. Heat only likes to flow from hot to cold. So in practice, we actually have to have the gas be infinitesimally hotter than the cold reservoir is. Okay. As the gas loses heat, and I can kind of draw here, There's our input heat coming. Let's think of this as being inside the system. We're going to make a closed loop around here. It's a convenient way of diagramming it. Now, at this cold temperature, we're dumping the waste heat. How do we do it? Well, in order to, as the heat would flow out, if we held the gas at a fixed volume, it would want to lower its temperature. As heat flows out of it, the internal energy would decrease. And if we're not doing any work on the system, then, well, that means that its temperature would go down. But we can't have that because the heat won't flow. So we've got to maintain the gas's temperature infinitesimally above Tc while it loses heat, which means it has to be compressed. An isothermal compression. And again, just like I showed in step 1, this means to hold the gas temperature fixed, if the temperature is fixed, the energy is fixed, so du is 0. Notice the sign here, because it's losing Qc, plus the work done in step 3. Okay, so that 0 equals that plus that. So Qc equals negative integral of the pressure over the, which is a function, over step 3, integrated over the volume. And you solve that, and you find out that the change in volume over step 3 has got to be negative, so it's actually got to be compressed. This is an isothermal compression. So here we are dumping the waste heat out into the environment at a temperature Tc. Okay. Finally, we've got to get our gas back up to the high temperature to complete the cycle and be ready for the next step through. So step 4, let's see here. We're going to take the gas from temperature Tc back up to Th in preparation for the next cycle, because we don't want heat flowing in or out for that matter, but I guess we couldn't, over this here, because we don't want to create any new entropy. We've got to have Q be 0. Okay, to make that 0, then Q has to be 0, which means it's adiabatic again. And looking back in chapter 1, because adiabatic curves always curve down to the right, then that means to connect this point with this point here, that's awfully steep, really. Trust me, it's close. We've got to be going up and to the left. An adiabatic compression. And that completes a Carnot cycle. That is the most efficient that any heat engine can be. So, if that's the most efficient a heat engine can be, we should all go out and put Carnot engines into our cars and run around. We'll save so much money, we'll get so much better gas mileage because we're not wasting any, we're not creating any new entropy in the process. The most efficient we can do. Not a good idea. And this is where discussions on economics and engine design and so on like that have really got to be taken into account, because a Carnot engine, well, if you maintain your gas's temperature infinitesimally below your high temperature reservoir's temperature during your isothermal expansion, it's a very slow flow of heat because the temperature difference is so tiny. Heat flows more quickly when there's a big difference of temperature. Heat flows very slowly when there's a small difference of temperature. So the isothermal expansions and compressions are extremely slow processes. That means that, your expansion and compression strokes of the engine are very slow. And while you get wonderful gas mileage out of a car running on the Carnot engine, as the book points out, the little old ladies with their blue hair and their walkers on the sidewalk will be passing you and making comments about how slow your car is. So it's not a good idea. There is great efficiency in this, but very low power. Energy transformed into work over time. Okay. Let me show you, though, an example of a kind of engine which has an efficiency which in some analyses I've read, theoretically it is equivalent to a Carnot engine under idealized conditions. And that's called the Stirling engine. And that's the dash on. I won't be analyzing it here. We can get onto it in a later on in the chapter. But it's a really neat engine. It is high efficiency, low power, but it's useful in a lot of ways because, unlike an internal combustion engine, the Stirling engine, there we go, is an external combustion engine. It can use whatever heat source you want. So I've got here a little model Stirling engine. This is just a flywheel here. Its construction has it with here is the piston, all right? As the pressure increases, it pushes that piston out, which turns the crankshaft and the flywheel. I should hold that down here. All right, that's the piston there. In order to change the internal state here, the crankshaft then also pushes this, which is a displacer. This is not a piston inside, that black styrofoam there. That's actually a loosely fitting displacer that simply shoves the air from the hot side to the cold side. Actually, I'll have this the hot side and that the cold side. So this one is designed to run at very low temperatures, which is why the odd shape. I'll hold it above this hot plate, and this model was made very poorly out of plastic, which, because plastic is an insulating material, is not great for absorbing or getting rid of heat. But I'll hold it over this here. This is hot but not burning at this level here. The problem about Stirling engines is that they need a little kick to get them to start going. Now, by the way, how do you know that that's going on its own and it's not just me doing it? Well, if I try to go the other way, I'm working against the flow of heat and it stops. And now you see it advancing correctly. This design of Stirling engine is able to run on a temperature difference of about 5 degrees Fahrenheit, maybe a little bit more. You can, and I have done it, set it on a cup of hot coffee and watch it spin around. Hopefully I haven't melted anything on the plastic there. I'll put it on the hot plate. Very low power, but it'll run. And there are high temperature Stirling engines which need an actual flame right underneath them, which will run at much higher power. But these are a lot of fun. There are hobbyists who make terrific brass models of these things with literal candle power for them, and 4 or 6 pistons and such, all working off a common crankshaft. And because the pressure inside is very close to atmospheric pressure, it's not a high-pressure engine, which is the whole idea of the Stirling engine. They're very safe to work with, and they don't require extremely fine machining. You've actually got a little bit of slot between the piston and the cylinder here. It's not exactly airtight. Some people have made Stirling engines using plastic syringes and test tubes and a set of marbles. I'll have to link to some videos on those. Okay. That's it for today then.